Welcome for today's lesson. Today, again, we are going to talk about the subject by the name Microprocessor Systems. We want to see what happens with our processes, which are using in our computers and mobiles and so many things. So, a microprocessor systems. So it means there are many systems, but they are using a process which is very small, very small. So our today topic, basically topic 1, we shall talk about introduction. To microprocessor systems. So under this, let us try to define what's a microprocessor. Basically, the way I've said in simple terms that for Arithmetic language, micro means small, processor means something which can do what? Which can be changing information from one variable to another. So a microprocessor is basically a multi-programming device which takes what? Binary data as inputs, processes, it can have memory to store, and also can give you what? An output. So basically that's a microprocessor. That a system or a device which is a multi-programming device. Multi means many programs. So a multi-programming device which takes binary data as inputs, which means zeros and ones, then process it or change it to this format, then can store it in memory, or can give you an output. So there are various types of microprocessors which are in the market. Right now we have the Intel. Intel, they have many. Intel. So we have Intel 880, stroke 885. We have Intel 8086, that's another one. We have Intel 8088. We have Zero. Right now there's one they call Z80. We have microcontroller M6800 series. This is a microcontroller. There are many series under this one. So these are basically the most common types of microprocessor which we have. But for our lesson, we shall be talking about what? Intel 8080/85. Like now, before I even start, I want to tell those students who are suffering with what? Microprocessor programming. This is the way. This now, if we go to JEMSHAH, you shall be getting our programs. How we write the programs. People are wondering how they are able to do what? To write this program. Even the lecturers, if you have a problem, go to our website, which is JEMSHAH what? Then you get all the information, how the programs are being written. Then from there you can teach your students, or if you are a student, you can teach also your fellow students, or now you can understand what? So they don't have any problem. So welcome to this one, because now after doing the introduction, next as we are proceeding, we shall go to programming. So that now we read all those programs which have problems, so that at least you as a student you can understand, and then you can implement them in most organizations. Now, basically most processors, they should have memory, they should have a central processing unit, then we should have what? I/O devices. Let's talk about block diagram of a microprocessor. So let me draw the diagram here of a microprocessor. So a microprocessor should be made of a central processing unit, the CPU, which cannot work without being triggered. And for us to trigger here, we can have our crystal. So we have our crystal oscillator here, connected here, for synchronization and triggering crystal oscillator. Then from our processor, we can have the memory here, primary memory. And when we talk about primary memory means ROM and RAM. Then you can have the I/O ports, which will be also connected to I/O devices. So here we have primary memory, which is in bracket ROM/RAM. Then we have I/O ports. Then we have I/O devices. Sometimes people call them what? Peripherals. So now, how do we connect this CPU to this one? So we should have what? Buses. And we shall be defining the functions of each. And have buses here. Others are unidirectional, others are bidirectional. And I will tell you why others are bidirectional, others are unidirectional. So this one, this is the control bus. This one, which is bidirectional, is the data bus. Then we have the address bus. How are they connected? Now, this one will be only one way. So it will be giving control signals to the primary memory. Same to these I/O ports. This one way. But the data bus should be bidirectional, two-way, because we are transferring data to and from memory to the CPU and vice versa, or from the I/O ports. So again, I will connect them here. Just connect them here. So those are jumper wires, basically. Then what's remaining? The address lines. I can put them here now, the address lines, because they are the one to show us the memory where data has come from, and they are bidirectional. Yeah, they are unidirectional rather. And also I can connect them there. These are the address lines. Then from there, because now the I/O devices will communicate to the CPU via what? These I/O ports. So now this is our connection. Then you can have also analog devices down there. But basically, majorly, I wanted to draw this so that now, let me draw down here. We can have, for us to communicate with the analog devices, we can have the converters DSC or dark stroke ADC. Then you can connect it to the analog devices. Analog devices. So also they can make that way. And then I draw this one is unidirectional. This should be bidirectional. Then this is unidirectional. So you hear that with the aid of a rainbow diagram, describe the block diagram of a microprocessor. You can basically draw this. Now, let us see what's happening. We have the crystal oscillator. We have the central processing unit. We have the primary memories, which is ROM/RAM. We have the I/O ports. We have the I/O devices. If you are keen, the I/O devices have to communicate via the I/O ports in the microcontroller systems. Then we have the analog devices. Also, they have either to convert from digital to analog or from analog to digital using what? These converters. Now, let us explain the function of each block here. Now, for example, the crystal oscillator. The work of the crystal oscillator is to ensure that it has triggered the central processing units so that it can function on, and also is supposed to do what we call synchronization. It synchronizes the transfer, the control signals, they are moving. So anything which is happening in this system here, it is being synchronized by the crystal oscillator. What we mean by synchronization is this way, that the CPU and memory or I/O ports are able to work at the same speed and are able to have what we call interoperability. They are working without any problem. So the functionality of the system. Then the CPU, the central processing unit, is made of, basically this one is made of the control unit. It's made of the control unit. And also it has what? Arithmetic, logic unit, we call it in simple terms ALU, and registers. So the control units, this one, the control unit is the one which ensures there is all communication in between here, because the CPU is the heart of the microprocessor or of any small device. So the control unit is supposed to have the timing signals, generate them, transfer them, control the transfer of information, be it data or some instruction back to and to the memory, is the work of this control unit. Then as the name is suggesting, arithmetic logic unit. This unit is supposed to perform all arithmetic and logic functions. Arithmetic are things like what? Addition, subtraction, multiplication, multiplication. Then you can have looking for cosine, sine, all those. Then also logical functions, things like what? Nanding, oring, noting, all those we talk under dictionary about those gates. The oring, the anding, the noting, and others are performed by this unit known as what? Arithmetic and logic unit. Then we have the registers. Operations to be done here in this system of ours, it requires one to have registers, or our processor to have what? Registers. Things like accumulator, which is supposed to do what? These arithmetic operations. Then things like what? Registers, the general purpose of what? Registers. So when we talk about registers, it means these are where the data can be held temporarily, waiting to be processed, or for us to do any manipulation of data, we require these registers. So the CPU will have these three, and each we have said its own function. Then from there we have buses. We have the buses, and the buses are three of them. The way we've said, number one is the address bus. We have the data bus, and we have the control bus. So let us describe each will do what. In general terms, when they say buses, if you just say buses, then you say they are used to either transfer signals, control signals, or data to and from. So buses are able to basically to interconnect, or they are like the interface between the CPU and other blocks like now memory and I/O devices. So the address bus each has different function to perform. The address bus, as the name, if you see the word address, it means it's supposed to obtain the address or the memory location where data is retrieved from or will be stored to. So it's supposed to locate the address. If you are keen now, that's why you see the address bus is only unidirectional, which means it is the CPU who wants to transfer data to somewhere, someplace. So it is supposed to be located via the address bus. The data bus will carry data to memory or I/O devices from the CPU, or will obtain data from the I/O devices through the ports to the CPU, or from the memory to the CPU. That's why if you are keen in our diagram, it's on the data bus, which is what? Bidirectional, to transfer data to or to retrieve data back to the CPU. Then we have the control bus. The control bus is supposed to do what? To transfer some timing or control signals, so that now some functionality or operations are done what? Are controlled in our system. So the way the name is suggesting, control is supposed to transfer data. Like now, for example, let us go for our practical. That we have our system here. We want maybe there is an analog device like a printer here, and our printer is throwing printing our whatever we have sent to it. So what happens is that this CPU has to send some controlled information to guide us at what speed is our printer able to do what? To print, so that our data can't be lost in our organization, or we are able now, the analog device, which is the printer, is able to run at the same speed with the CPU. So the CPU will be forced, because of maybe this one can, like for example, I can send 10 megabytes per second. But my printer here, the analog device, is only able to print what? 100 kilobits per second. So after we have done what we call synchronization, both of them have done that way. So our system here will be forced to operate at the speed of what? That printer. Now, those are the function of what? Different buses and their functions. Like now in the exam, you can be hearing state 3 buses using what? Microprocessors. Address bus, data bus, control bus. Those are the 3. And their functionality, we have said each what's supposed to do. Then we talk about what? Memory. So our memory, primary memory, we have what? Why we say primary? It means we can have secondary memory. Things like what? Memory cards, flash disks, we got them what? Secondary memory. That's why If you are keen here, we are talking about what? Primary memory, since they are in the system. Because now secondary can be connected, maybe via our ports. So the primary memory ROM histogram, right now ROM will store what we call firmware. Firmware are the instructions from the manufacturer. They can store firmware. So memory, it means it can store data, process data, or instructions being used in our system. Then the I/O ports, they interface the processor with the I/O devices. So that's why if you are keen, the control bus, the data bus, the address bus are not connected directly to the I/O devices, but we have to pass through the ports so that we are able to communicate with I/O devices. Then now we have the analog device. It means if it's analog, it's not able to communicate with our processor, so we have to convert data back to digital when we are transferring to the processor, or back to analog when we are transferring to the analog device. That's why we see there are converters here. Digital to analog. It means this is the data transferred from the processor or the microprocessor to the analog device. Analog to digital. From here, it comes being analog. It has to be converted back to digital so that now they are able to communicate, because here we need what? Zeros and ones, or data in digital form. So basically this is now our system, the way it will be appearing. So once we enter in, we shall be talking about the different functions, and when we do programs, now it will be easier to someone to understand what happens in what? The different microprocessors. Now, after doing that, I can go direct to registers, which are talked down here, types of registers which are available in different processors. And note there, before we go there, remember, the types of inter. Like now I can draw a table here. There's a table I want to draw before I go to types of registers. So this is the type of a processor. Then this is the data size or data word. It's also sometimes common. You can see that table 1 shows the different types of processors. So complete the table by saying the address range, not the data bus, but the address range. Address range. It's a very commone also, address range. So we can have 8085, 8086, 8088, and also you can have microcontroller series. But these are the common ones. And then you can have MC1600 series. So right now the 885 address ranges are 16, 886 also they are 16, but this one has 20, this one has 16. So in case of this, there's a small question in there. Just know the number of address ranges in each processor. Now, types of registers. So there are two types of registers. There are two types of registers available in most microprocessors. Types of registers. We have what we call general purpose registers. So our major discussion will be under Intel 80/885. So our general purpose registers are registers like B, C, D, E, H, and register R. Then we have special registers. Special registers. So if you hear the word special, it means there is some function they are doing which this one cannot do. One of them, you can have the accumulator here. We can have the flag register. We can have the flag register. We have another register we call the stack pointer. The stack pointer. And then we have the program counter. Program counter. Or in the bracket they say PC. So why we call them special, the way I've said is there's some which they can do, others are not able to do. So these two types of registers right now describe the two types of registers available in what? 885 or most microprocessors. General purpose registers, it implies that these registers are being used in the system anyhow or anywhere without any what? Without restrictions. So right now register B, C, D up to R in 880/885 are general purpose registers. The special registers, let us try to define each will do what. Let us have the accumulator. The accumulator. Another name for the accumulator, you might get some books, they call it temporary storage register. Storage register. So this one will do what? So we say this one, the first thing it's supposed to do is to hold one of the data being processed, the accumulator, and also the result of any operation. So that's why you call it temporary, because like now when you want to do, we want to see when you want to do addition of two variables, like now that's 6 plus 20. For the microprocessor will do this operation, then the result of that operation will be stored in the accumulator temporarily. So it is the accumulator or temporary storage register. We have the flag register. The flag register will hold some flags which will be seen as trying to show conditions which are going to affect our processor or our operations. Like now, in 8080/85, we have different types of what? Flag registers. We have the carry flag, which we label as CY. We have the zero flag, which you say is Z. We have the sign flag, which you call S. We have the parity flag, which you call what? P. Like now, the carry flag will indicate whether there was a carry during addition or there was no carry. If there's a carry, we say the carry flag is set. So in most students who are doing this whatever the discussion, you might be hearing like an instruction, jump, no carry. It means, was there a carry? That's not a condition. So we can say that the flag register will hold some flags which are going to be used to test some conditions in our operations. Carry flag, to test whether there was a carry or not. And we have agreed, if there is a carry, this carry flag will be at logic 1. If there is no carry, it will be at logic 0. Zero flag, it will test if the result is 0 or not 0. Like now, for example, if I'm adding FF in hexadecimal plus 0, 1. So remember in hexadecimal, if it is 16, F plus 1 will be 16, 0, 0, and then there is a carry 1. So for your information, the carry flag here will be set because there is a carry. And because the result is 0, also the 0 flag here will be set at logic 1. So at least at this operation of addition of FF plus 0, 1, there are two flags being what? Set. The carry flag, because this plus this, we get 0, 0, carry 1. The carry flag will be set, there's a carry. And the zero flag, because the result is 0, also it will be set. So once the result of an operation is 0, the zero flag will be set. If there's a carry, the carry flag will be set. So we shall use this one to test some conditions. The sign flag. The sign flag will be indicating whether the result is positive or negative. Remember, we are talking about when we do things like in digital electronics, we talk about what? Signed and unsigned numbers. So the sign flag will be indicating whether the result is positive or negative. Then we have the last one, which you call parity. Let me write it, this one in full. Parity. Some people ask, what's parity? Parity basically is the number of ones in a bit stream. Number of ones in a bit stream. What do you mean by bit stream? Bit stream is the bits. Like now, if I have 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, this is a bit stream. So the number of ones here, these ones we are seeing here. So the number of ones can be odd or even. So that's why you see now, after talking about the number of ones in a bit stream, we can talk about either even parity or odd parity. So what do you mean by this one? For example, if we have data like what? data like 1 0 1 0 1 1 0. Then use even parity. So a parity bit will be added depending whether the number of ones are odd or even. So if I was even parity, I would count 1 2 3 4. Because the bits are even, so I will add 0 to maintain what? My parity being even. If somebody was using what? Odd parity, using the same bits, I don't want to change. Someone was using odd parity, let us count the number of ones. Remember, if they are even, and you're using even parity, you add 0. 1, 2, 3, 4. Because we are using odd parity, so that they can assist the transmission, we add what? 1. So 1, this is not useful data, this one is useful data, but it will assist us during transmission, particularly to test for errors. So now these are what? Parity bits. So now in microprocessor, we shall see us talking about jump parity odd or jump parity even, depending on which one you are using. So now, if you are keen from what I've discussed here, it implies what? It implies this way. This flag register contains some flags which will be testing the conditions of any operation, be it arithmetic or logic operations. Then from there, we talk about the stack pointer. The stack pointer, in simple terms, most books they call it SP, the stack pointer. So if you see here the word pointer, it means this is something pointing somewhere. So we say in simple terms that it is a register being used to point at the top of the stack memory. The stack memory, where you want to see later when you want to do about stack operations, the stack memory basically is what we call stack memory. Is basically a file where we store data. Stack memory is known as a LIFO file. So LIFO file means last in, first out. So it means there is a way, in such a way that this memory, once we store programs there, there is a way that the one which we stored last will be the first one what? Out. This is where now we want to talk about some instructions which some students don't understand, which you talk about push and pop what? Instructions. We shall see when you want to do programming, what's happening in the stack memory or the LIFO file. So the stack pointer is the one to point at the top of the stack, and the stack memory will be appearing this way. This something like this. Then now you might get that if this is the top, then our stack pointer will be pointing here. By a certain instruction, I don't want to go there, by maybe saying RXI SP somewhere. So it will point at the top of the stack. And then mark you shall realize that most processors, the stack memory is always up to the top. Near, if you are for example from 0 0, if you are most like now in 8 8 up to FFFF, if this is your memory you want to use, you might realize that from the stack memory will start from F00H to FFF. So maybe that is starting there. Why we put the top is that we don't want some operations which are used in subroutines operations to affect the normal running of what? A microprocessor. That's why we try to store this stack memory or operations or subroutines at the top, near the top. So basically why I came up to there is, I know when you want to talk about stack operations, we shall be talking about this stack pointer. Remember, make sure you remember, we talk that the stack pointer points at the top of stack memory. A stack memory is a LIFO file. Now, the program counter, PC. So the PC, or a program counter, will point to the memory location where the next instruction to be executed is found. And this stack pointer, rather program counter, you might realize, if you have done programming, that there is no instruction which will be incrementing what? The PC from one memory location to another. So we say that the program counter will point to the next memory location where the next instruction to be executed is found. And is incremented by 1 automatically after each execution of an instruction. So it is automatic, unless you want to jump out of. There no more. Then there's some instructions which you use when we talk about what? Branching from the main program to somewhere else. I want to draw the diagram which try to show the registers and how the number of bits in each register. So let us draw the diagram here so that you can see it clearly. So now the diagram is this way. This is our diagram. This diagram is very important for us to understand what's happening. Now we can have the registers here. You have then in between we have register A. It goes together with F. Register B and C. We have D and E. Then we have H and R. Then there are two. We have the stack pointer and the program counter. In our diagram, this one is always 16 bits. But from here to here, this 8 bits. Now, so if you are keen from this diagram, there's a reason why I was drawing this one. It means this way, that all these registers, register A, which is the accumulator, the flag register, register B, register C, D, E, H, and R, all of them are always 8 bits. But the stack pointer and the program counter, and I repeat again, the stack pointer and the program counter, they are always 16 bits. From the diagram here. So this diagram will try to show you clearly the number of bits in each register. The A up to R are 8 bits. Stack pointer and program counter are 16 bits. Now the question comes, what if I have data which is what? 16 bits. So we might realize that register B will be combined with the C. So we call them BC, DE, and HR. So that now when you want to write programs, you get that we say RXI B, which implies BC, or DE, or HR. A, when combined with F, it forms a certain register we call PSW. So in case in your learning, we have seen something like this. This in full is processor status word. A word is always 16 bits. Status is always 8 bits. And the processor is the accumulator because it's the one which processes. So maybe there's something we forgot to say, some definitions. Like now, if we talk about a bit, a nibble, byte, then one. These are terms which you use in most processing systems. A bit is one variable, either 0 or 1. So it can be either logic 1 or logic 0. A nibble is always 4 bits. So when you hear about a nibble, it means 4 bits. A byte is 8 bits. And then a word is 16 bits or 2 bytes. Sometimes some others call them 2 bytes. Because it is known as processor status word. What shows the condition or the status of anything is the flag. The processor is the accumulator. The accumulator is made of 8 bits. The status or the flag register is known as what? Is made of 8 bits. So a word is 16 bit. From where? The status 8, the processor what? 8. So that one also has come to our note that the flag register, sometimes this flag register, another name for flag register is the status register. Because it tries to show some states of some conditions. It's also known as the status registers. So basically, these are the registers which are going to use in our programming. So make sure you understand the different functions. State the function of the accumulator, stack pointer, program counter. Make sure you understand. General purpose registers, we are talking about B, C, D, E, H, R. Then there's another register which you talk about. You can hear somewhere we talk about memory address registers, MAR, memory address registers. They are used, these are 16-bit registers, being used to point to the memory location where data is retrieved from or saved to. So we call them memory address registers. Then also there's another register which we have not talked here, which is not under this one, which we call instruction register, IR. There's another register they call it that way. Instruction register, IR, in bracket, instruction register. So the instruction register is, what the function of this one is, to hold the instruction. To hold the instruction which is being decoded, and executed, which is being decoded and then executed. Which means what? In what we talk about, maybe I'm going to talk next before our lesson is off, in what we call fetch execute cycle. Once we fetch an instruction, most processors, they don't fetch only one instruction. Most processors, because they want the speed to be higher, we fetch more than one instruction at a time. Then once we fetch them, we put them in a pipeline so that they will be waiting to be decoded and then executed. So the instruction register function is to hold that instruction which is being decoded. Another name for decoding is to be interpreted before being executed. So what happens in most systems is that, or in most processors, we fetch more than one instruction at a time, then we put them in a pipe or in the pipelining. So the process of executing more than one instruction at a time is what they call in, you might get this word somewhere, instruction pipelining. What is this? This is the process of fetching more than one instruction at a time so that they can be put somewhere in a pipeline waiting to be executed. We use this type of fetching of instructions so that we make our processors what? High, to run at what? High speed. Instead of fetching one, we wait for it to be decoded, then to be executed next, then we fetch another one. It will slow our systems. And remember, there's a lot of data to process these days. So what we do, we can fetch more than one. We can even fetch what? How many instructions? 8 to 16. We put them somewhere in a pipeline. They will be interpreted and then executed. Once they are over, we fetch more again, 16 of them. So that way, you might realize that our processor is of what? Higher speed compared with what? Others. And it is most systems now, they prefer what? This instruction pipelining. Now after that, I want to talk about fetch or the instruction cycle. Also is also common, the instruction cycle. What happens there in the instruction cycle? So the instruction cycle has 3 processes. So I can start here. The first process is I fetch. You fetch the instruction. Then you decode. Another name for decoding is to interpret. Then you execute. You execute. If you are fetching only one single, if there are many, then you can have a condition here. You ask yourself, are all instructions fetched? If yes, I hope those who have done, but we shall come later to flowcharts. If yes, you stop. If yes. If no, we go back to fetch another one. If no. But if it was only one instruction, then I'm going to have said fetch, decode, execute, then you stop. But because we have agreed that most systems, or most of the time, we don't fetch only one instruction. So what we do, we fetch one instruction, we decode or we interpret, we execute, then we ask ourselves, are all instructions fetched from them? Maybe the memory? No. Go back. If yes, stop. If no, so here now we can have amen, we were fetching. If there are 10, we can have a counter, we do the necessary. So basically, sometimes this is what we call instruction cycle. So if you hear that we did a diagram describe instruction cycle, you draw this, you talk about fetching of the instruction, interpreting or decoding, then you execute. So now, in our introduction part basically, make sure you remember about the block diagram of a microprocessor, then functions of various blocks in the processor. After that, also we have talked about the different types of registers. We have realized there are two types of registers, the special the registers and general purpose registers. In 8.8/85, we have agreed that general purpose registers include register B, C, D up to register R. Special registers are things like accumulator, which I also referred as temporary register, flag or status register, stack pointer, and the program count. And we have defined each does what in the microprocessor. Also, we have talked about instruction register, and I've said that the IR register is used to hold the instruction during decoding and execution. And then under that one also, we agreed that most systems these days, they don't fetch only one instruction. We fetch more than one instruction at a time in a process we call what? Instruction pipelining. So in most exams, you might hear that they say define or describe instruction pipelining. So you say that is the process of fetching more than one instruction at a time. Then you decode one instruction at a time as others are waiting in the pipeline or somewhere, someplace. So that's instruction pipelining. Then lastly, again, we are talking about what? Instruction cycle. The process of getting the instruction from memory up to the time it will be interpreted, then it will be executed to do what? A certain function. I've drawn the diagram or the waveform or the timing diagram to show what's happening and the conditions and also the operation or the process in each. When we want to do some programs and a flow charts, then this is when I'm going to explain these blocks means what. We want to use different blocks in flowchart programming. So after we have understood now that what's the processor will do, or the microprocessor. Now once we have understood the functionality and what is entailed in the processor, now at least we shall be moving to programming, where before we shall enter to programming, we shall talk about the different types of what? Instructions, like now data manipulation. And I know this is where most students or most people have problems in programming. So like things, we want to see things like move immediate, MVI, MOV, then we shall apply them here, we write programs. Once we are through, I'm hoping and have my faith that people will be understanding that programming is what easy. Once you understand the instruction, will do what and what they are supposed to be doing. So when we shall meet next, and I am urging you to make sure you go to JEMSHAH, you see what's happening. Next lesson, we shall now go into programming, the types of instructions which you use in programming, and then now we start writing the programs. And for you to write these programs, make sure you understand how to convert what? To convert numbers from analog, we convert these numbers from decimal to hexadecimal. Our 88/885, we shall be using what? Hexadecimal. So that you can be seeing things like what? Well, I'm going to write things like when we meet, maybe move immediate A to 0H. So this H, it will be implying what? That our data is in hexadecimal. Like now, this is 32 in decimal. So we shall do a recap on conversion of numbers from decimal to hexadecimal. Then now we enter to our programming, we do our programs, and once we are through, we are very sure in JEMSHAH that you will be able to understand how the programs are being written, and the problem which most students will be having here, I hope that we shall be done and we shall assist many. Thank you so much for the lesson today. Let us meet next.